In 4.4, we're going to look at two ideas. One of them is on spanning sets, and the other is on linear independence and dependence. So if we look at an example, let's say R2. R2 is a set of all vectors x, y, where x and y can be any number. So you can think of those as any possible ordered pair. We can express, we can say that these two particular vectors span that set, and what we mean by that is we can attain any possible vector in R2 using a combination of those. For example, if I want the vector 5, 7, then I could take 5 times the first vector plus 7 times the second vector. If I want the vector 8, negative 9, I can do 8 of the first vector minus 9 of the second vector. And that'll give me 8, 0 minus 0, 9. 8 minus 0 is 0 minus 9. And notice that gives us that vector. So we can say that these two vectors span R2. They can be used to write any vector in R2. But that's not the only set of vectors that span R2. This is, let's see, that's the standard basis. We'll call that a basis, and we'll talk more about what bases are later. But this is the standard basis. The standard set of vectors that are used to span R2, but there are lots of other ones. I think in this section, instead of the standard basis, they call it the standard spanning set. We could look at a set of second degree polynomials and lower, and we could say that they're spanned by 1x and x squared. If you want to list any polynomial that's second degree or lower, we can form that with a combination of those. For example, if we want to list the polynomial 3x squared plus 2x plus 5, then we would take 3 of the x squared vectors, 2 of the x vectors, 5 of the 1 vectors. Again, this is the standard spanning set, but it's not the only set that could be used to span all second degree polynomials or lower. So one thing we're going to be asked to do, we'll be given a set, and we'll be asked, do these vectors span a certain particular space? So let's look at an example. Let's look at the set 1, 2, 3, 0, 1, 2, negative 2, 0, 1. And let's see, does this span R3? So we want to see, can we take something times the first vector plus something times the second vector plus something times the third vector and get any possible vector in R3. Now we could use different notations. The book calls these U1, U2, and U3. You could do X, Y, and Z, RST, whatever you wanted to. But this just stands for any random vector in R3 where U1, U2, U3 could be anything. So basically, if we can find a relationship between A, B, and C, and U1, U2, and U3, then if you tell me what U1, U2, and U3 are, then I can give you the A, B, and C that correspond to that. Now, to start with, if we're just wanting to see if they do span, then we just want to see, is there a solution to this system of equations? So first of all, let's write out the system of equations. So if we add the first elements together, we get A1, no B's, minus 2C's. That equals the first element here. And then the second elements, we have 2A's plus 1B plus no C's. That equals the second element. And then 3A's plus 2B's plus 1C. And that equals the third element. So if we were to take this, row reduce this, then we can find a correlation between A, B, and C, and U1, U2, and U3. But if we're only looking to see, is there a solution to this? Is there a linear combination of these such that we can form any vector? Then we're just wanting to see, is there a solution to this, or is this not possible? So if there's a solution to this, then when we take our, there are several ways to show if there's a solution. One, we could see, does this have an inverse? One, we could row reduce it, see how many pivots we have. What the book actually does is they take the determinant of the coefficient matrix. So let me pull up MathCAD and let's take that determinant real quickly. All right, so I went ahead and opened up MathCAD, put in our coefficient matrix, took the determinant, and when we got the determinant, we got -1. Now recall that if the determinant is not 0, that means that A does have an inverse, and if A has an inverse, then there is a solution to the equation AX equal B. On the other hand, if the determinant would have been 0, then there's not an inverse, which means there's not a solution to that. So we found out, hey, there is a solution to AX equal B. Now our solution will more or less be a relationship. How are A, B, and C related to U1, U2, and U3? But if you gave me specific numbers, U1, U2, and U3, then I could tell you for those particular U's, these are the A, B, and C that we would need to get those. So since there is a relationship here, then in fact these vectors do span R3. Now they give another example, and we'll kind of compare these to see that this next set does not span R3. 1, 2, 3, 0, 1, 2, which is the same so far, but now negative 1, 0, 1. And let's show that this does not span R3. So if I do A times the first one plus B times the second one plus C times the third one, if that spans R3, that should give us any possible three-dimensional vector. This time I'm just going to use X, Y, and Z. So if we write that system out, we get 1A1, no B's, minus C is X, 2 A's, 1 B, no C's is Y, 3 A's, 2 B's, 1 C is Z. So if there's a solution to this, then this set of vectors also spans R3. If there's not a solution, then it doesn't. So if we look at our coefficient matrix, 1, 0, negative 1, 2, 1, 0, 3, 2, 1, let's see what the determinant of this is, just to check to see if there is a solution. Remember, the determinant equals 0 means there's not a solution. Determinant not 0, there is a solution. So our first two columns are the same, but let's change the third column, first entry, to negative 1. And now when we take that determinant, we get 0. So the determinant does equal 0, which means there's no solution, no general solution for this. So we can't get a correlation between A, B, and C and X, Y, and Z. So we can't just take any random point and write it as a linear combination of those three vectors. We can obviously get some vectors by linearly combining those. If I just take the first vector plus the second one plus the third one, I get an answer, but I can't get every possible vector in that set. So this demonstrates that it's not possible to get every possible vector, not just any vectors, but every possible one. If we were to row reduce this, we would have a 0 row, or we would get zeros on one side and a number or letter on the other side, so there wouldn't be a general solution to this. So let's look at one or two more examples before we go on. And we'll look to see, well, what is the relationship? Let's see. Let's do this one. Let's take the point 2, 1, or the vector 2, 1, and the vector negative 1, 2. And let's see if it spans R2. So let's see, can we take something times the first vector plus something times the second vector and get any possible vector in R2? So just as a reminder, this is called a linear combination, taking a scalar times a vector plus a scalar times a vector. That's called a linear combination. So this yields 2A minus B equals Z, A plus 2B equals Y. So if we want to actually find out what the solution or what the relationship is between A, B, and X, Y, let's solve this by row reducing it, by doing Gauss elimination with a homogeneous, not the homogeneous, with the augmented matrix. So let's take our coefficients. So here are our coefficients. This is what the equation is equal. And let's solve this. So let's begin. Let's swap the first two rows, which is another way of saying swap the rows, I guess, since there are only two rows. Now let's do minus 2 times the first row plus the second row. So if I do minus 2 times 1 plus 2, that gives us 0. 2 times negative 2, that's minus 4 minus 5. Y times negative 2, that's minus 2y plus x. So then if we want to get a 1 here, do negative 1/5 R2, or you could say divide by negative 5. So that gives us 1, 2, y, 0, 1. We could call this x minus 2y over negative 5. Or you could move the negative up top and make that a minus and that a positive. Now if we want a 0 here, we can do negative 2 times the second row plus the first row to get our new first row. So keep the second one. So negative 2 times 0 plus 1, negative 2 times 1 plus 2, and then negative 2 times this, so negative 2 times negative 1, so 2x minus 4y over 5 plus the top one, and that yields our R1. All right. So if we want to, we could get a common denominator here, call this 5y over 5. So this would be 2x minus 4y plus 5y, so plus y over 5. So that's, remember these are a and b, so that's what a is. B is 2y minus x over 5. So a couple of points here. Notice we got a solution. When we set this equal to the generic xy, there was a solution, and we found that there was. We not only found that there was a solution, but we found what the solution was. So it does span, these two vectors do span R2. And this tells us how they span. We'll later call this a basis, but let's look at an example. If I want to attain the vector 3, 5, remember x and y are my generic vector a and b, it tells us how many of this vector and how many of that vector does it take to get the vector I'm trying to achieve. So if I'm trying to achieve 3, 5, then A would be 2 times 3 plus 5 over 5. B would be 2 times 5 minus 3 over 5. So 11/5 and 7/5 is what we need to get 3, 5. So let's try that. So what were we? 2, 5, and then not 2, 5, 2, 1. And then our other vector was negative 1, 2. So let's verify that if we take 11/5 of the first vector, 7/5 of the second vector, that does give us 3, 5. So 11/5 times 2, that's 22/5. 11/5 times 1, so 11/5. 7/5 times -1, that's -7/5. 7/5 times 2, that's 14/5. So if we add those together, we get 22/5 minus 7/5, which is 15/5. 11 plus 14 is 25/5. 15 over 5, 25 over 5, which, yeah, that's what we were trying to get. So this just establishes relationship between x and y, a and b. You tell me what point we're trying to get, x and y, and I'll tell you what a and b need to be by plugging in, and that'll tell us how many of each of these vectors does it take to get that random point in R2. So that's the first idea here, checking to see if two vectors span a particular vector space. And the second idea that we're going to look at here is linear independence. So let's look at an example. If I have the vector 1, 2, I add that to the vector 2, 4, we get 3, 6. So 3/6 is a linear combination of those two vectors. So if we were to have the set 1, 2, 2, 4, 3, 6, this set of vectors would be considered linearly dependent because one vector is a linear combination of the other two vectors. So anytime we can write one of the vectors, it doesn't matter which one, we could have written this as a combination of those two vectors by doing this vector minus this vector. That would have given us that. If we can write one vector as a linear combination of the other two, then those are said to be dependent. One is tied to the other ones by some linear combination. On the other hand, if we have a set of vectors and there's no way that we can linearly combine two of those vectors to get the third vector, if there's not a solution there, then these are said to be linearly independent. So we'll go through some examples and we'll look at, well, what's the best way to test to see if a set is dependent or independent? Now, if we have a set that's only made of two vectors, it's really easy to see whether they're dependent or independent or not. If we have the vector 1, 3, and 2, 6, if there are only two vectors in our set, the only way they could be dependent is if one is a multiple of the other. Notice if we take the first one and multiply it by a scalar, we get that one. So these are said to be dependent on each other. They're tied together. They're so closely related that one is the other one scaled up. Same thing if we have a three-dimensional vector. If one is a scalar multiple of the other, then they're dependent. Notice if we take 5 times the first one, we get the second one. On the other hand, if we have two vectors and they're not scalar multiples of each other, notice to get this one, I would have to double the first component, but if I also double the second one, that doesn't give me 5. So these would be independent. So if you have two vectors, or it could be two matrices, we could have a set of matrices. I could have 1, 1, 0, 1, 2, 2, 0, 2. If we only have two elements in our set, two matrices, two vectors, two polynomials, then for them to be dependent, one has to be a multiple of the other one. So notice if we multiply the first one by the scalar 2, we would get the second one. So in this case, they would be dependent. However, if we change this element to 3, then this matrix is not a scalar multiple of this one, so they would be independent. Now, if you get beyond two vectors or two matrices, it gets a little bit more complicated, but we'll look at that now. So let's suppose we have three vectors, or three matrices, or three whatever. Could be 4, could be 5. So if we could rewrite the first two as a linear combination to get the third one, then these would be dependent. On the other hand, if there's not a way to combine the first two and get the third one, then they would be independent. So instead of solving our system in this form, what actually turns out to be easier is to subtract this from both sides, and let's give it a scalar. And since our scalars could be either positive or negative, let's just call that plus c. That would leave us 0 on the other side. So let's go back and think about this again. So if there is no solution, then they're independent. So notice this is homogeneous. So if the only solution to the homogeneous is a trivial, which means A, B, C equals 0. So if the only solution is trivial, the trivial solution, then they are independent. Because again, if the trivial solution is the only solution, that means there's not a solution for this, and if there's not a solution for that, then they're independent. On the other hand, if there are solutions to the homogeneous equation, that means there are ways that we can relate those vectors, and if there are ways we can relate those, then they are dependent. So let's look at an example. Let's see if I can find one. Let's look at the set 3, 4, negative 1, 1, 2, 0. So let's see if we do A times the first one, B times the second one, C times the third one. Let's see if the only solution to that is the trivial solution. So that means that 3A's minus a B plus 2C's equals 0, 4A's plus a B, no C's equal 0. So we're going to do Gauss elimination with the augmented matrix 3, -1, 2, 0, 4, 1, 0, 0. And we're going to see, is there just a trivial solution to this, or are there multiple solutions? If we row reduce this, then we're going to end up having two pivots. So if we have two pivots, then it doesn't matter what our third value is, but the only solution that we're going to have will be our trivial solution. Actually, let's hold on just a second. That's not so. Let's swap these around. Let's put 4, 1, 0, 0 on top, 3, -1, 2, 0 on bottom. And let's take the top one, let's divide it by 4. So we get 1, 1/4, 0, 0. And then let's do -3 R1 plus R2 to get our new R2. So 1, 1/4, 0, 0. Sorry, phone's ringing. So if we do that, we get a 0, -3/4 plus 1, so -7/4, 0, 2, 0. So we do have two pivots. We can't possibly have three pivots if we have two rows. So let's multiply this bottom row by +4/7 so that we get a 1 here. So 1, 1/4, 0, 0, and let's make it negative. 1, -8/7, 0. So if we call these A, B, and C, then notice C is a free variable. C can be anything. So what we said earlier was that for them to be independent, we had to only have the trivial solution, which is where A, B, and C all were 0. But here, A would be 0. If A were 0, B were 0, C could be anything. So that's not going to quite exactly work out. If you think about it like this, B is 8/7 T. A is -1/4 B. So basically, you tell me what C is, I'll tell you what A and B are. So there are solutions that are not the trivial solutions. Hence, this one is not independent, but rather it's dependent. So just for example, if we let C be 1, then B would be 8/7. A would be -1/4 of that. So 8/7 times -1/4, that's -2/7. So that would be an example of something that is a solution to that homogeneous system, which means they are dependent on each other. So I guess let's just go back real quickly and let's illustrate that. In fact, we can take two of these vectors and write them as a linear combination of the other ones. So if we have, this said we had -2/7 times the first one. B was 8/7, so 8/7 the second one plus the third one equaled 0, 0. Or that also meant that we could subtract this from both sides. So that means those first two equals the opposite of that last one. Or if we multiply through by a negative there, so do multiply through by a negative, we get a positive there, a negative there, we get that. So let's see. We check to see if this is true. 3 times 2/7, that's 6/7, 8/7. Negative 8/7 times 1, that's 8/7, minus 8/7. Notice if we combine these, 6/7 plus 8/7, that's 14/7, which is 2. 8/7 minus 8/7 is 0. So this is a linear combination that gives us the third vector, so they are in fact dependent. So that's going to be our goal in all of these. If we can put these together and show that the homogeneous has a solution, then they're dependent. If the homogeneous only has the trivial solution, then they're going to be independent.